Hello friends, my name is Rohan Goyal and I am your civil engineering faculty at Engineering Hotspot. So in today's lecture, we are going to look at a GATE 2020 set 1 marks question. Let us first read the question. What does it say? A reinforcing steel bar partially embedded in concrete is subjected to a tensile force P. The figure that appropriately represents the distribution of the magnitude of bond stress represented as the hatched region along the embedded length of the bar is. Now the question is asking us what is the distribution of the bond stress along the length of the reinforcing bar. The first question that arises in the student's mind is that what is bond stress? Do you know what is the basic meaning of bond stress and how does it helps in the concrete designing, structural designing? So let us first study what is bond stress. Bond stress is the bond resistance achieved by the tangential shear stress component along the interface between concrete and the reinforcing bar. Let us understand this through a diagram. Let us take the same example as also the question. So we have given in the question that a concrete block has been given and a reinforcement bar is embedded into that concrete block. Now a load P, tensile force P, is applied to the bar. Now this bond resistance is a tangential shear stress component. Which acts along the interface between the concrete and the reinforcement bar, that is along the surface of the steel which comes in contact with the concrete. Now this is bond resistance offered by the interface which results to bond stress. As we all know, stress is the result of strain. So the variation of this bond resistance itself is asked in the question, which diagram depicts the actual distribution of the bond resistance. I'll give you the answer, but I think you students need to know the bond resistance in a better detail before you come to the answer. Now, what is this bond resistance? Where does this bond resistance come from? This bond resistance comes from three factors. First is chemical adhesion. During the hydration of concrete, gum-like components are formed, which provide the adhesion between the reinforcing steel and the concrete, which contribute to bond resistance. The second factor that contribute to bond resistance is frictional resistance. Due to the surface roughness of the reinforcement bar and the concrete that comes in contact with the reinforcement bar, there a resistance is developed at the surface, which also contributes to the bond resistance. The third factor that contributes to the bond resistance is mechanical interlock. If a ribbed bar is used as the reinforcement, which have protruding on the surface of the bar As in the case of HYSG bars, let us see with the diagram what actually does the ribs imply. Suppose this is a reinforcement bar and you will find ribs on the surface of the bar. Now these ribs provide interlock between, gets interlocked in the concrete and provides additional resistance as bond resistance. Now this bond resistance is expressed as tangential force per unit nominal surface area. Now why have I written nominal surface area is because while expressing this bond resistance, this surface area, additional surface area due to this protruding is not taken into account. Hence, we use only normal surface area during the analysis of bond resistance. That is the hash portion as shown in the diagram above. That is Newton per mm square or megapascal. Now, this is the basic. What is bond stress? What is bond stress? Now, coming to the practical significance of bond stress, without bond resistance, the basic assumption that we take in the analysis of both limit state method and working stress method, that the plane section remains plane after bending, wouldn't be applied, wouldn't have been valid. It is because of this bond resistance itself that that assumption stays valid. Due to bond resistance, the axial force in the reinforcement bar gets distributed to the surrounding concrete, ensuring composite action and strain compatibility. क्या होता है, reinforcement bar जो होती है उसमें जो टेंसाइल स्ट्रेस या कंप्रेसिव स्ट्रेस होता है वो इस बॉन्ड रेजिस्टेंस के थ्रू सराउंडिंग कंक्रीट में डिस्ट्रीब्यूट हो जाती है, जिसके कारण क्या है, एक कंपोजिट एक्शन मिलता है हमें विद बोथ कंक्रीट एंड स्टील टुगेदर. Hence, the strain compatibility is ensured through bond resistance. Now, this bond resistance is induced in two cases. First is flexural bond. We can say this is the first case in which the bond resistance shows its application. Now, when a beam is subjected to bending, due to bending, there may be cases in which the movement is varying along the length of the beam. Now, due to this variation of movement along the length of the beam, the tensile or the axial stresses may vary along the length of the beam. Now, this variation is induced in the reinforcing bar because of the bond resistance. Had this bond resistance not been there, there would have been uniform axial force along the length of the bar, as in the case of strings, or in the pre-stressed concrete, we are providing a reinforcing bar without any bond with the concrete. जब एक बीम पे फ्लेक्सर मूवमेंट्स अप्लाई होते हैं ड्यू टू किसी लोडिंग कंडीशंस, डिफरेंट टाइप ऑफ लोडिंग कंडीशंस के कारण, या फिर सपोर्ट्स के कारण, डिफरेंट टाइप ऑफ सपोर्ट्स के कारण, the beam में movements की variation हो सकती है, and due to that variation of movements the tensile or the compressive stresses in the reinforcing bar may also vary. We will study all these things in detail, but for the question practical. But in order to tell you the practical significance of the question, I'm just introducing to you in brief what is the application of bond stress. और जब ये axial stresses vary होते हैं along the length of the reinforcing bar, which is ensured through bond resistance. This bond resistance is ensuring the variation of axial stresses in the reinforcing bar. Had this, अगर ये bond resistance ना होता, तो along the whole length of the reinforcing bar, the stresses would have been constant. As in the case of string or suspended cables. Now first is the flexural bond that we have seen how the bond resistance plays a role in flexural bond, and second is anchorage bond or development bond. Now this bond comes into picture when there are bar endings, reinforcement bar endings or cutoff points. Let us take an example of a cantilever beam. Now let this be our cantilever beam subjected to a load W at the free end. And this is the end section of the cantilever beam. Okay. Now now because of this load W, we will get tensile force in the top fibers of the beam, due to which if the reinforcement is not provided, as we all know that concrete is weak in tension, we will get cracks in the top fibers of the beam, as you can see. You will get cracks in the top fibers of the beam. In order to arrest these cracks, we provide reinforcement so that the steel reinforcement will take tensile force. Now, let us provide the steel reinforcement. Now, the tensile force that will act in the top fibers of the cantilever beam will be taken by the steel reinforcement. But you might have noticed that I have ended the bar in the cantilever beam itself. I haven't extended it into the column. Now, because of this, what will happen is at this point, the bending moment will be maximum. So this is the bending moment diagram of the cantilever beam. Now, suppose this is of length L, the beam is of length L. So the bending moment will be maximum at the end of the cantilever, negative, because it will be hogging bending moment. So because the bending moment is maximum, the tensile force in the bar will also be maximum. Now at this point you can see that if we take just the bar, if we maximize this, and if we magnify this portion, at this point we are getting At this point, we are getting maximum stress, Pmax. Beyond this point, beyond this point, there is no bar to take the tensile force. Hence, the tensile force will be taken by concrete at this section, due to which we will get cracks in concrete, and hence our cantilever beam will fail. In order to ensure that the reinforcement bar takes all the tensile force, we have to extend this reinforcement bar into the column so that an appropriate development length is provided to the reinforcement bar so that the bond resistance is able to normalize the maximum load at this point. So this maximum stress will be resisted by the bond resistance offered by the development bar that is embedded into the concrete. And this same case and this same question is been asked in the GATE 2020. Just take this much portion of the column and you will get your question. So now coming back to the question, now it has been observed experimentally that the stress is bond resistance or the bond stress is maximum at the starting of the embedment, and it shows and it has been seen experimentally that the bond stresses follow curve as shown in the figure C. This experiment you can do yourself also. Pull your finger by holding it like this, try to pull your finger. You will feel that the maximum resistance offered by your finger and the interlock of your hand will be maximum the at this end, and it will go keep on reducing to the other end. And you can see in the exam itself also that how these technical knowledge that you gain through books can be applied practically in the real life also. Hence, option C is a correct option. But while designing, we assume that the bond stress is uniform throughout the length. IS codes have given appropriate values for both WSM method and LSM method separately. And by using those values, we get conservative results for calculating the development length. This has been done to simplify our calculations and to simplify our designing. So this is a brief about bond stresses. I hope you like this lecture. Do comment and tell if there is any scope of improvement. I will really appreciate your comments and I'll try to improve on it. Thank you. See you in the next lecture. Goodbye.